Hello fellow problem solvers. So they're already doing a problem from the 2003 IMO, problem number 4. This is a beautiful geometry problem I'll try out if you're someone getting more comfortable in geometry. You've done the junior level competitions and now you want to get to the IMO. This is a great problem to try out for a minimum of 30 minutes, ideally 45 to 90 minutes, not more than 3 hours. And if you'd like to go along with us, give us a go for the next 20 minutes. Put your first ideas out on paper. Look at this condition. What does it mean? And now without further ado, let's begin. So we have this cyclic quad. Okay, let's draw a circle. Boom. And now let's do, we're going to have A, we're going to have B, we're going to have C, and we're going to have what else? We're going to have D. Kaboom. Cyclic quad. And now we're going to be putting the feet of perpendiculars here, kaboom, a foot of perpendicular here, and a foot here, boom. And these are called, what's called BCCAAB, so PQR. And we must show that PQ is QR if and only if the angle bisectors of these two ABC and ADC meet on AC. Okay, so this is a very cool problem, and I want to ask you this. Let's solve the problem sort of backwards. Let's think backwards instead of saying, what do we have from these being, this being equal to this? Let's ask, actually if we have an if and only if, it's both forwards and backwards. It's just depending on what you look at. But let's look at what this really means. I think this is the, like when two things are equal, we sort of, yeah, we kind of know what that means, but what does it mean for two angle bisectors to be concurrent on AC? So let's see what that means. If we have a circle, kaboom, and now if we have A, C, B, and D, what does it mean? It means that we have an angle bisector here, and this is also the angle bisector. So this angle is equal to this one, this is equal to this one, and they meet at some point E. Now, what does this mean? I invite you to pause for 5 minutes and ask yourself, what can you infer from this about ABCD? Pause now. And the answer is, you have, from the angle bisectors, mind you, you have that, for the angle bisector theorem, you have that BA over BC is equal to AE over EC, right? From the angle bisector theorem on this triangle, ABC. However, in the triangle ADC, you have that AD over DC is also this over this. So this is in fact equal to AD over CD, right? Now, what does that tell us? Well, it tells us that AD over CD is equal to BA over BC. Now, this is what holds true if they meet, if their angle bisectors meet. Now, the next sort of question to ask ourselves is, if this holds true, do the angle bisectors meet? Right? It's sort of like you're trying to go both ways. See, like, how can I use this fact? Like, mind you, this is a fact of concurrency, and you have to find a way to extract some information from that about the configuration. Extract some information about the configuration. And if you want, I invite you to pause for 3 to 5 minutes and see, does this over this equal to this over this imply that the angle bisectors meet at AC? And the answer is yes, it does. And the way we can actually show that is say we have AD is equal to, say we have this is equal to this, right? Then what we can do is we can intersect this angle bisector with AC, call this point E, and then we have this is equal to this, but this is also equal to this, right? And now we have AE over EC is AD over DC, and now we have, by the converse of the angle bisector theorem, that ED is in fact the angle bisector. So here in our problem, we want to prove like we have an equality. Here we want to translate this condition into inequality, we're going to prove that PQ is QR if and only if, what's it called, AB over BC is equal to AD over DC, right? This is what we want to prove now. And now let's look at a problem forwards. Let's see, what is it that we have? First and foremost, before we even look at the conditions, like these equal to this, let's see what do we have from this configuration, from R, Q, and P. Is there anything specific, given this is a cyclic quad, right? Because, mind you, the thing about E, we haven't used the fact that A, B, C, D is a cyclic quad. And you can try to figure out if there's a way to use it. I frankly don't see it just now. So maybe there's something about this being a cyclic quad here. Let's try and see. So the first thing to do in this situation is what? Chase some angles, figure out what's going on here. And I invite you to do just that for the next 15 minutes. And now here's what I see. So what we have is, say, let's calculate some angles. So we have this angle, QRD, is equal to QAD, okay? Now QAD is the same as CAD, and CAD is the same as CBD, right? Now we have CBD. Can I get anything else from here? Actually, yes, I have the cyclic quad DPBR, and that gives me DBC is DBP, and that DBP is equal to DRP. So we have that this angle is also equal to that one. In other words, we have PQR are collinear. And we have that because this is a cyclic quad, we've used the fact that this angle is equal to this one. So we know that PQ and R are in fact collinear points. And now let's try to look at what does the problem tell us. So we have that if this is the case, then Q is the midpoint of PR. It's an interesting claim. What do we have from the angles? Let's see like more angles. What do we have? We have this angle is equal to this one, is equal to this one now. And then this angle given, what is this? PQC, we have PQCD. So this one is equal to this angle right here. Okay, that tells us something. Perhaps nothing, but it feels like it could tell us something. And actually, if we pay close attention, actually I don't know if it tells us anything, to be frank. What is this angle equal to, is my question. I have a hint here for what could be the case. And I invite you to pause for 3 minutes and ask yourself, do you see anything that you're that's telling you maybe something could be the case? Explore that. Like, that's what geometry is really about. You need to explore these configurations. So I have this angle right here is on one hand DQPC equal to this angle, which is equal to BCA, which is equal to this angle, which is equal to actually this angle right here. So I have, now I'm a bit suspicious about what it is I've gotten. Let me double check, because I've gotten that if this is 90 and this angle is equal to, but this angle isn't equal to, this angle is equal to this angle. Okay, yeah, that makes sense, because these two angles are equal. I thought for a second that this whole angle would be equal to this angle, but it's not. So we have that these angles are also equal. QDA and BDC, or BDC, is equal to QDR. Could there be something there? We don't know yet. And now maybe let's look at this condition. What do we have from PQ is QR. And this is a midpoint. And I'm really suspicious about the fact that, what's it called? I'm suspicious about the fact that this was at a 90-degree angle, right, on AC. So it feels like there should be something more to this story. And I can't have this fully. Can I have this angle anywhere else? I have the angle, actually, the angle BDC. Okay, let's like name these angles. X, X, Z, 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 and X right here. And then we have a Z right there and X right there. A, B, C. No, I've messed something up now. No, this angle isn't X. This angle is, this is X, but this one isn't. So this is all 90 minus X, 90 minus X. And this whole thing is 90 minus Z. This is 90 minus Z, which means this whole thing needs to be 90 plus Z. So this is Z minus X, Z plus X actually, which makes sense because this is Z plus X. And that seems about it. That seems about everything that I'm getting now. Now, PQ is QC, is QP. Can we get this is equal to, like we could potentially, if we wanted to, like call this angle Y. We could calculate trigonometrically now. This QP is equal to the sine of x plus y, that's equal to this over the, whatever this angle is equal to, which is equal to this angle, which we can also calculate, but this is 90 plus z. So this would be 90 minus x minus z minus y. So that's what this angle would be equal to. And then we could have that angle is equal to this one. And wait a second though, that angle is equal to, though I've said here that this is 90 minus, it's not 90 minus z, it's 90 minus z minus x minus y. And then this one is also 90 minus x minus z minus y. And now we have, say, QP, actually, so QP over the sine of this is equal to, say, the cosine. We can have QD over the cosine of x plus y plus z, right? Or the sine of 90 minus x minus y minus z. And we have that also QR over sine of x plus z is equal to QD over this angle right here, which is equal to cosine of x. Like this is 90 minus x, so the sine of that is cosine of x. And now QP is equal to QR. If and only if, due to these two things, we have sine of x plus z over cosine of x is equal to sine of y plus x over the cosine of x plus y plus z. And now it must probably be the case that these sines, in fact, give us this condition over here. Yeah, we can just finish this trigonometrically. Is that what I see now? And I invite you to actually pause for 10 minutes and try to do that. And here's the next step. And the answer is you have, what's it called? And we have, when we do the sine theorem on the quad ABCD, we'll get that this whole thing holds true. And now if we plug that in instead of these sines, we plug sine of x plus z over cosine of x. We'll plug, what do we have? Sine of x plus z over cosine of x. We'll have is then equal to CB over CD. And then here we'll have is equal to AB over AD. And then we're done. Now if you're thinking, wait a second, I don't know trigonometry that well, there's also a way without trigonometry that we could go about solving this problem. Could go about trying to find this similarity and trying to find this actually. And that is through the use of some similarities and some, what's it called, menelaus theorem. So for example, we could say, let's take advantage of the fact that these are collinear. How can we do that? Well, we can apply menelaus theorem to see what happens. And the reason we want to also apply this is because Q is the midpoint. So we'll apply it to the triangle BRP and the lines the points AQC. And then we'll have that actually. We'll have PQ over QR. So now what do we have? We have PQ, QR. Then we have times RA over AB times BP over PC. We have this is equal to 1. And we want to show if this is equal to 1, if this right here is equal, that we're going to have this on the other side. What do we have here? We have PC. PC is here. We have Z. We have Z. We have PC. We have RA. These things are corresponding in these two similar triangles, ARD and what's it called? CPD, because of the angle Z and a 90-degree angle. So we have that actually. RA over PC is equal to AD, RA, PC, AD over CD. And on the other hand, what do we have? We have BP and AB. Actually, you have BP, P, AB. Oh, it's not BP, it's my bad. It's not BP. It's B, wait a sec, what are the lines? It's this triangle, it's BC over AB. Yeah, it's BC over AB. Let's see, I have a Q here and A here, APC. Yeah, that's what it is, BC. And now, given this, when you apply menelaus, you have this, and then you're done. Really, then the condition, then you have for menelaus and the similarity that, what's it called, PQ over QR is equal to, so if we, instead of writing RA over PC, we'll write, actually let's do this, times AD over CD times, what's it called, BC over AB is equal to 1. And now we have, if this is the case, then this thing right here is 1, and then these two things are equal. Or if these two things are equal, then this is 1, and then we have this. So those are like two ways of going about it. There's a trigonometric way, but there's also a way of saying, wait a second, how do I use this fact that these are collinear? You say, okay, let me apply menelaus. Why do I want to apply menelaus as well? Well, it's because I'll get BA over BC, which is also what I need, and I'll be able to use this condition. That's why you apply it on this triangle. Could you apply it on another triangle? I think probably not. Maybe there's another way to apply. I'm taking on a triangle with D. Is there a way to apply it there? I think very difficult because D is like forming these P, Q, and R, like you're getting feet of perpendicular, so it would be very hard to connect them. But I may be wrong. And these are the two ways to solve this problem. The reason I like the problem is because it first has this idea of, okay, this is a wacky condition, right? When you first see it, if you've never seen it before, it's wacky. It's like, wait, what? How do I prove that? And then you take a step back and you see, okay, so what is enough and what I need is this angle, is this side condition. And then you go ahead and try to see, okay, forwards I have, these are collinear. This is actually the Simpsons line that has a name, right? If you want to explore that of the, like whenever you put a point on a circle of the triangle ABC and you put all the feet of these perpendiculars, they will be collinear by doing the similar thing we've done here. And from there on, you go, okay, how can I use this fact? One way is I can just mark where all the angles and do trig. And the other way is saying, wait a second, let me use the fact that these are collinear. Let me apply menelaus, because menelaus will give me AB over BC. If I applied correctly, so we applied on this triangle, because I can also use this, have this condition within the Menelaus theorem. And then I see, okay, I have AR and PC are kind of pains in the asses. And then I say, oh, okay, but I have similarity here, that I can get AR over PC, which is also what I have in my Menelaus, to be AD over DC. And then you see, okay, I'm done. Right? That's sort of like these progression steps here. Now, the important part, what it teaches you is also, like, reiterates this principle of just like having your angles and then seeing, okay, I have them, now what do I do? And you're trying to like extract as much as you can from these angles. Now, this finishes up our problem, and as always, thanks for problem solving.